grinding is an abrasive machining process that uses a grinding wheel as the cutting tool. A wide variety of machines are used for grinding: hand-cranked, knife-sharpening stones, handheld power tools such as angle grinders and die grinders, various kinds of expensive industrial machine tools called grinding machines, bench grinders often found in residential garages and basements. Grinding practices a large and diverse area of manufacturing and tool-making. It can produce very fine finishes and very accurate dimensions, yet in mass production contexts it can also rough out large volumes of metal quite rapidly. It is usually better suited to the machining of very hard materials than is regular machining, and until recent decades it was the only practical way to machine such materials as hardened steels. Compared to regular machining, it is usually better suited to taking very shallow cuts, such as reducing a shaft's diameter by half a thousandth of an inch at 12.7 micrometers. Grinding is a subset of cutting, as grinding is a true metal cutting process. Each grain of abrasive functions as a microscopic single-point cutting edge, and shears a tiny chip that is analogous to what would conventionally be called a cut chip. However, among people who work in the machining fields, the term cutting is often understood to refer to the macroscopic cutting operations, and grinding is often mentally categorized as a separate process. This is why the terms are usually used separately in shop floor practice. Lapping and sanding are subsets of grinding processes. Selecting which of the following grinding operations to be used is determined by the size, shape, features and the desired production rate. Surface grinding. Surface grinding uses a rotating abrasive wheel to remove material, creating a flat surface. The tolerances that are normally achieved with grinding are plus or minus 2 times 10 minus 4 inches for grinding a flat material, and plus or minus 3 times 10 minus 4 inches for a parallel surface. The surface grinder is composed of an abrasive wheel, a work-holding device known as a chuck, either electromagnetic or vacuum, and a reciprocating table. Grinding is commonly used on cast iron and various types of steel. These materials lend themselves to grinding because they can be held by the magnetic chuck commonly used on grinding machines, and they do not melt into the wheel, clogging it and preventing it from cutting. Materials that are less commonly ground are aluminum, stainless steel, brass and plastics. These all tend to clog the cutting wheel more than steel and cast iron, but with special techniques it is possible to grind them. Cylindrical grinding. Cylindrical grinding is used to grind the cylindrical surfaces and shoulders of the workpiece. The workpiece is mounted on centers and rotated by a device known as a drive dog, a center driver. The abrasive wheel and the workpiece are rotated by separate motors and at different speeds. The table can be adjusted to produce tapers. The wheel head can be swiveled. The 5 types of cylindrical grinding are: outside diameter grinding, inside diameter grinding, plunge grinding, creep feed grinding, and centerless grinding. A cylindrical grinder has a grinding wheel, 2 centers that hold the workpiece, and a chuck grinding dog, or other mechanism to drive the work. Most cylindrical grinding machines include a swivel to allow for the forming of tapered pieces. The wheel and workpiece move parallel to one another in both the radial and longitudinal directions. The abrasive wheel can have many shapes. Standard disc-shaped wheels can be used to create a tapered or straight workpiece geometry, while formed wheels are used to create a shaped workpiece. The process using a formed wheel creates less vibration than using a regular disc-shaped wheel. Tolerances for cylindrical grinding are held within 5/10,000ths of an inch for diameter and 1/10,000th of an inch for roundness. Precision work can reach tolerances as high as 50 millionths of an inch for diameter and 10 millionths for roundness. Surface finishes can range from 2 to 125 microinches, with typical finishes ranging from 8 to 32 microinch. Creep feed grinding. Creep feed grinding was invented in Germany in the late 1950s by Edmund and Gerhard Lang. Unlike normal grinding, which is used primarily to finish surfaces, CFG is used for high rates of material removal, competing with milling and turning as a manufacturing process choice. Depths of cut of up to 6 mm are used along with low workpiece speed. Surfaces with a softer grade resin bond are used to keep workpiece temperature low, and an improved surface finish up to 1.6 micrometers are max. With CFG it takes 117 sec to remove 1 in 3 of material, whereas precision grinding would take more than 200 sec to do the same. CFG has the disadvantage of a wheel that is constantly degrading, and requires high spindle power, 51 horsepower, and is limited in the length of part it can machine. To address the problem of wheel sharpness, continuous stress creep feed grinding was developed in the 1970s. It dresses the wheel constantly during machining, keeping it in a state of specified sharpness. It takes only 17 sec to remove 1 in 3 of material, a huge gain in productivity. 38 horsepower spindle power is required, and runs at low to conventional spindle speeds. The limit on part length was raised. High efficiency deep grinding uses platted superabrasive wheels, which never need dressing and last longer than other wheels. This reduces capital equipment investment costs. HEDG can be used on long part lengths, and removes material at a rate of 1 in 3 in 83 sec. It requires high spindle power and high spindle speeds. Peel grinding, patented under the name of Quick Point in 1985 by Erwin Juncker Maschinen und Fabrik GmbH in Nordrach, Germany, uses a tool with a superabrasive nose and can machine cylindrical parts. Ultra-high-speed grinding can run at speeds higher than 40,000 fpm, taking 41 sec to remove 1 in 3 of material, but is still in the R&D stage. It also requires high spindle power and high spindle speeds. Others form grinding is a specialized type of cylindrical grinding where the grinding wheel has the exact shape of the final product. The grinding wheel does not traverse the workpiece. Internal grinding is used to grind the internal diameter of the workpiece. Tapered holes can be ground with the use of internal grinders that can swivel on the horizontal. Centerless grinding is when the workpiece is supported by a blade instead of by centers or chucks. 2 wheels are used. The larger one is used to grind the surface of the workpiece, and the smaller wheel is used to regulate the axial movement of the workpiece. Types of centerless grinding include through-feed grinding, in-feed, plunge grinding, and internal centerless grinding. Pre-grinding: when a new tool has been built and has been heat-treated, it is pre-ground before welding a hard facing commences. This usually involves grinding the OD slightly higher than the finished grind OD to ensure the correct finish size. Electrochemical grinding is a type of grinding in which a positively charged workpiece in a conductive fluid is eroded by a negatively charged grinding wheel. The pieces from the workpiece are dissolved into the conductive fluid. Electrolytic in-process dressing grinding is one of the most accurate grinding methods. In this ultra-precision grinding technology, the grinding wheel is dressed electrochemically and in-process to maintain the accuracy of the grinding. An ELID cell consists of a metal-bonded grinding wheel, a cathode electrode, a pulse DC power supply, and electrolyte. The wheel is connected to the positive terminal of the DC power supply through a carbon brush, whereas the electrode is connected to the negative pole of the power supply. Usually alkaline liquids are used as both electrolytes and coolant for grinding. A nozzle is used to inject the electrolyte into the gap between wheel and electrode. The gap is usually maintained to be approximately 0.1 mm to 0.3 mm. During the grinding operation, one side of the wheel takes part in the grinding operation, whereas the other side of the wheel is being dressed by electrochemical reaction. The dissolution of the metallic bond material is caused by the dressing, which in turn results continuous protrusion of new sharp grits. Grinding wheel. A grinding wheel is an expendable wheel used for various grinding and abrasive machining operations. It is generally made from a matrix of coarse abrasive particles pressed and bonded together to form a solid, circular shape. Various profiles and cross-sections are available depending on the intended usage for the wheel. Grinding wheels may also be made from a solid steel or aluminium disc with particles bonded to the surface. Lubrication. The use of fluids in a grinding process is necessary to cool and lubricate the wheel and workpiece, as well as remove the chips produced in the grinding process. The most common grinding fluids are water-soluble chemical fluids, water-soluble oils, synthetic oils, and petroleum-based oils. It is imperative that the fluid be applied directly to the cutting area to prevent the fluid being blown away from the piece due to rapid rotation of the wheel. The workpiece. Work-holding methods. The workpiece is manually clamped to a lathe dog, powered by the faceplate that holds the piece in between two centers and rotates the piece. The piece and the grinding wheel rotate in opposite directions, and small bits of the piece are removed as it passes along the grinding wheel. In some instances, special drive centers may be used to allow the edges to be ground. The work-holding method affects the production time as it changes setup times. Workpiece materials. Typical workpiece materials include aluminum, brass, plastics, cast iron, mild steel, and stainless steel. Aluminum, brass and plastics can have poor to fair machinability characteristics for cylindrical grinding. Cast iron and mild steel have very good characteristics for cylindrical grinding. Stainless steel is very difficult to grind due to its toughness and ability to work harden, but can be worked with the right grade of grinding wheels. Workpiece geometry. The final shape of a workpiece is the mirror image of the grinding wheel, with cylindrical wheels creating cylindrical pieces and formed wheels creating formed pieces. Typical sizes on workpieces range from 75 in to 20 in, and 80 in to 75 in length, although pieces between 25 in and 60 in diameter and 30 in and 100 in length can be ground. Resulting shapes can range from straight cylinders, straight-edged conical shapes, or even crankshafts for engines that experience relatively low torque. Effects on workpiece materials. Mechanical properties will change due to stresses put on the part during finishing. High grinding temperatures may cause a thin martensitic layer to form on the part, which will lead to reduced material strength from microcracks. Physical property changes include the possible loss of magnetic properties on ferromagnetic materials. Chemical property changes include an increased susceptibility to corrosion because of high surface stress.